Hello everyone, I am Nitish Deshpande, fourth year student in UC San Diego. Today I will share my research on the topic Achievable Rate of a SISO System under Wideband Matching Network Constraints for the Globecom 23 conference. This work is in collaboration with Professor Castellanos from UT Knoxville, Professor Robert Heath from UC San Diego, and Saeed, Jingfeng and Harish from Nokia Bell Labs. I will start by discussing the motivation of this work. With every wireless generation, there is a transition from narrowband to wideband to support more data rate using more bandwidth. In this work, I am focusing on the hardware bottleneck that arises when we scale the bandwidth. I am specifically focusing on the transmit matching network block in a SISO link. The matching network is like a filter which can transfer power from the radio frequency chain to the antennas. For a narrowband system, this filter is approximated as a frequency flat response. For a wideband system, we can no longer approximate this filter as frequency flat because of its frequency selectivity. In this plot, I show what happens if we incorrectly model the matching network for wideband system. Here, the blue curve shows the achievable rate as function of the bandwidth for the ideal case, which is the frequency flat assumption. Whereas this curve shows the achievable rate when we accurately model the frequency response of the matching network. For this simulation, I have considered a simple conjugate matching circuit. We see that for narrow bandwidth, the frequency flat model works very accurately. However, as the bandwidth increases, we start to see the deviation of the achievable rate for both these models. This plot shows that it is very important to accurately model the frequency selectivity of matching network as wireless systems transition from narrowband to wideband operation. In our research, we are focusing on the problem of maximizing achievable rate under wideband matching network constraint. In this plot, we had showed that the ideal Shannon bound is not realistic for wideband system. So then we asked the question of what is a more realistic bound? So in this presentation, I will address this question of what is the achievable rate upper bound obtained with the frequency selective matching network model. In our work, we want to obtain very general results and do not want to limit the results to a specific matching network topology. So for this, we will use Bode-Fano bounds from the microwave literature. The second question is, once we derive this upper bound, how do we propose realistic matching network designs to approximate this achievable rate upper bound? Another observation from this plot is that there is an optimal bandwidth beyond which the achievable rate starts to decrease. So is it possible to improve this optimal bandwidth with better design strategies that we obtain from our approach? And how does that approach compare with the conventional conjugate matching technique? So the overall focus of this talk is advancing wireless systems with communication-centric methodology to design wideband matching networks. Let us look at the conventional approach for designing matching networks from a conventional antenna and circuit theory perspective. Consider a simple dipole antenna for which we have a lumped element approximation. A traditional approach to design matching network is to minimize metrics like return loss or maximize power transfer efficiency based on a simple circuit model. This technique works only for narrowband metrics, as is shown in reference 1. There are a few extensions for designing matching networks for wideband using the Smith chart method. However, the limitation of this approach is that it ignores the frequency selectivity due to other components in the RF chain. For example, the wireless channel can also be frequency selective for wideband systems. So we take a fundamentally different approach to designing matching networks. Our approach is rooted in communication theory. So we look at the end-to-end communication link. In this work, we are focusing only on a single input, single output system, where we have an ideal wideband signal transmitted from the RF chain and received at a single antenna. Each block in this link is a frequency selective filter. So in practice, the signal gets distorted in the frequency domain as it passes from the antenna through the wireless channel and received on the receive antenna. So this is how the power spectral density of the received signal looks like in frequency domain. So the metric from communication theory that we use is the achievable rate, which is integrating the spectral efficiency over the desired bandwidth. So how do we model this system with circuit theory approach? Since this is a SISO link, we will model the communication link using a two-port network. At the transmitter, we assume a voltage source which models the signal at the output of the transmit radio frequency chain. The matching network is modeled as a two-port network. Similarly, the transmit antenna, wireless channel, and receive antenna is also modeled as a two-port network. On the receiver side, we abstract the receive RF chain as an ideal load. For representing these linear blocks in the circuit, we used the scattering parameter notation. And for defining the input and output signals, we are using the root power wave notation, which is very commonly used in the microwave literature. So this circuit theory approach allows us to physically define the power spectral density. This approach of modeling using circuit theory is an emergent technique of realistically modeling wireless systems. You can check out the recent magazine paper from our group for more details. Now let us look at the system model in detail. The transmit signal is denoted by this complex number AT of F, which is the incident root power wave, and the received signal is written in terms of BR of F. To capture the effect of matching network, we first define the ideal SNR, which is only capturing the scattering parameter of the wireless channel and the scattering parameter of the transmit antenna. So this SNR does not incorporate the practical effect of matching. This is called as the ideal SNR, which is traditionally used when matching is ignored. And then we use this metric called as the transmission coefficient, which captures the matching efficiency of this filter. So this is defined as the ratio of the power delivered to the load and the power supplied in terms of the root power waves. Now you can see that the achievable rate expression includes this product of the ideal SNR and the transmission coefficient. So this metric captures the effect of the wireless channel through the SNR ideal term and the matching efficiency through the transmission coefficient term. Now you can see that the structure of this objective is very similar to the conventional problem where we have a power allocation. But the only difference here is that unlike a digital filter where we can independently change the power for different frequencies, the value of this transmission coefficient are coupled for different frequencies. Now let us look at how we formulate an achievable rate maximization problem by applying constraints on this transmission coefficient. I will now discuss the constraints on the transmission coefficient. The first constraint is on the range of the transmission coefficient, which lies between 0 and 1, as follows from the definition. as it's a ratio of two variables. The second constraint comes from the Bode-Fano theory. I will start by discussing a simple example for a classical Bode-Fano limit. For a simple parallel RC load, the Bode-Fano theory gives an upper bound on this term in terms of the resistance and the capacitor. The intuition behind this bound is that practical antennas have reactive components, and as reactive components store energy, it's in a finite bandwidth. So that's why this upper bound is a finite number. If the transmission coefficient tends to 1, which means this integral will blow up and that leads to infinite bandwidth, that is impractical. So that's why practical antennas do have an upper bound prescribed by the Bode-Fano limits. So we are using Bode-Fano theory in this work because we want to generalize our results and not limit to a specific matching network topology. And that's why Bode-Fano theory gives general bounds based on the lumped element approximation of the antenna. For detailed calculation of how to compute the pre-log factor and the upper bound, you can refer to the paper by Bertrand Huckwald on bandwidth analysis of multiport radio frequency systems. I will now summarize the optimization problem. Our goal is to maximize the achievable rate, which depends on the ideal SNR and the transmission coefficient, which is subject to two constraints. The first constraint is a Bode-Fano constraint, and the second constraint is the range constraint. Our optimization variable in this problem is the variable tau-f, and we designed tau-f, the optimal tau-f, to maximize the data rate. So this is a new benchmark that can be used for designing the impedance matching networks instead of using conventional metrics like power transfer efficiency, which do not capture the end-to-end communication rate. The solution to this problem will be an upper bound on the achievable rate of a SISO system over all physically realizable linear and passive matching networks. Let us look at the simulation results for this work. In our simulations, we are considering a choose antenna at both receiver and transmitter. Here we show plots for two different target bandwidths. In the left plot, we are looking at the target bandwidth of 4.2 gigahertz. Here we see that the blue curve is the upper bound based on the transmission coefficient as 1, which is the perfect matching that corresponds to the Shannon bound that we saw earlier. This bound is not realistic for practical antennas. Our proposed upper bound, which is the orange curve, is more realistic as it incorporates the Bode-Fano theory into Shannon theory and is achievable for practical antennas and matching networks as given by these yellow curves, which is a simulation that we get from the ADS software. So the upper bound based on the Shannon and Bode-Fano theory can be easily realized by a simple matching network topology, which shows the practicality of our contribution. The right plot is for target bandwidth of 0.7 gigahertz. In both the target bandwidth plots, we see that the proposed upper bound is more realistic, and it also is above the conventional conjugate matching given by this curve. The conjugate matching solution is a fixed solution and cannot dynamically adapt for different target bandwidths, whereas our proposed solution can be optimized for different target bandwidths because it incorporates the end-to-end communication data rate. Finally, we move on to the achievable rate results with this new approach. Here, we reconsider the same plot that I discussed in the motivation slide, and now I add the proposed upper bound, which is the orange curve. We see that This bound is more realistic as it captures the gain bandwidth trade-off of the matching networks. The Shannon bound is overestimating the data rate as it neglects the matching constraint. The proposed bound is more realistic because it's closer to the rate achieved from the practical circuit simulated in the ADS software. The second observation is that the proposed bound also exhibits the optimal bandwidth trend. We also see that the optimal bandwidth has improved compared to the conventional conjugate matching technique. This means our proposed approach is more effective as it incorporates the achievable rate metric and allows to use more bandwidth and improves the data rate. Finally, we conclude the presentation by the key takeaways. Proposed upper bound based on the combination of Shannon's theory and Bode-Fano theory is more realistic because it captures the gain bandwidth trade-off of matching networks. We also show that from the derived theoretical bound and the ADS circuit simulation, there is an optimal bandwidth behavior that is observed in the achievable analysis as a function of the bandwidth. For future work, we propose the application of this methodology to other antenna types like dipole or patch antenna. In our journal paper, we also extend this approach to a MISO system. The extension to MIMO system is a direction of future work. Thank you, and I look forward to your questions and comments.